Hello everyone. In this set of videos, we're going to start discussing recurrence relations. These are going to be functions that call themselves, which if you've never seen recurrence before, is a strange thing. So if we look at this function, its name is factorial, and then within the function we are calling factorial. I'm going to assume that anyone watching this has seen recursion in the past. So if you haven't, I would recommend finding somewhere that you've seen that. We aren't going to talk a huge amount about specifics about recursion. We're going to assume that you have some level of knowledge of this already. The thing that makes this interesting is that the runtime for this is not going to be easily computable. There's a couple of things that are worth mentioning. The first thing is if n is equal to 0, something different happens than if n is not equal to 0. In particular, we might want to denote that, so I'm going to let t of n be the running time of factorial, be the runtime of factorial, with input n. That will be relevant in a second here for us. I know something from these first couple of lines of code. I can see that if we have n equals 0, we know what happens. So t, the runtime, if n is equal to 0, is what? In that case, what does the code do? Unambiguously, every time, what the code is going to do is check if n is equal to 0. That returns true if n is 0. And then it will return 1 every single time. So this runtime is constant. It's the time it takes to check if n is equal to 0, return true from that check, and then return 1 as a result of this. So that's one thing we know. This, however, is not helpful to us because all of our asymptotic notation assumes that n is effectively, for all purposes, infinitely large. We had this for all n greater than or equal to n not statement within our definition. So saying n equals to 0 isn't necessarily helpful to us as is. So this is what happens in our, what we call base case. All recurrences need a base case, otherwise they will run indefinitely. So our base case for this recursion is 0, and it takes constant time. We then need to try to figure out how to categorize the running time when n isn't equal to 0. So let's write that in a different color. We want to write t of n is equal to something when n is not equal to 0. Well, if n is not equal to 0, let's see what the code does. If n isn't 0, we check if n is equal to 0. That returns false, so line 2 would execute. We would then execute line 5 and then line 6. Line 2 and line 6 both take constant time. So let's say that C2 is the runtime for that constant. It could theoretically be a different constant than the constant for the base case. So I'm going to also differentiate the base case by calling that C1. So that C2 corresponds to the time it takes to check if n is equal to 0 and then return x at the end. We've still not dealt with the hard line of code there, though, the line I highlighted where we make our recursive call, where we call factorial. This is not necessarily 100% obvious. There's something that happens there as well, which is we're going to retrieve n and multiply by whatever this factorial thing does and assign it to x. So a lot of those things take constant time. Retrieving n, assigning it to x. The one thing that does not take constant time is our call to factorial. At least we don't know if it takes constant time. It takes, I don't know how much time. But actually, we do. We have an expression that tells us how long factorial takes. By definition, t of n is how long factorial takes with size n. So if I call factorial with input of size n minus 1, the time for that is going to be t of n minus 1. This may seem a little strange at first. What we're doing is we're saying there are two things that contribute to the time. The first thing that contributes to the time is the cost of checking if n is equal to 0, accessing n, all of the stuff that's the basic operations of this. And then in addition to that, we also make a recursive call, so we need to add on the time it takes to make that recursive call. So this first term, we're going to zoom in and label these, is what we call the cost of the non-recursive work. And then the second term is the cost of the recursive call of size n-1. So we have those two different things contributing to the runtime. I'm maybe going to format this a little better now that we have something written down. Move the C2 over. This, all well and good that I have something I've written down. It still doesn't help me, though, because I can't just say what this is in theta of. There's a t on both sides. I have no clue what t of n is doing still. So how are we going to deal with this? We're going to have a couple of methods. The first one we're going to introduce, people either call the expansion or substitution method. I usually call this substitution. I'm going to make the following observation. I'm going to first label this equation somehow so I can differentiate it. I'm going to put a little star next to it. What I am going to do is I'm going to plug n-1 into star. So we're going to, off to the side here, plug n-1 into star. And let's label that with a blue star. So on the left-hand side, I would get t of n-1 if I replace n on the left-hand side with n-1 is equal to C2 plus, if I plug in n-1 on the right-hand side, I'm replacing n with n-1. So this will be t of n-1 minus 1. This is t of n-1 is equal to C2 plus t of n-2. I am then going to replace the t of n-1 in the original equation with this new t of n-1. So if we look, I have t of n-1 over here. I also have t of n-1 over here. I'm going to replace the one in the dark blue equation with the right-hand side of the one I just developed. So we then replace t of n-1 in, I'm just going to call it star again, with the equation above. If we do that, we get t of n, taking our equation that we wrote in blue there, is equal to C2 plus I'm replacing t of n-1 with the right-hand side here, which is going to be C2 plus t of n-2. I wrote brackets there. We'll see this maybe later that becomes relevant. For now, we're just going to do that to say the stuff in brackets is exactly the same as all the other stuff that was in light blue. And now I'm just going to sort of do some basic algebra. I can let together the two like terms. I have two C2s. So t of n is equal to 2 C2 plus t of n-2. So now I have two different ways of writing down t of n. I have t of n is equal to the stuff in light blue. I have t of n is equal to the stuff in dark blue. And I also have that t of n is equal to this new expression I developed down here. What are we going to do now? Because this didn't help us. We still don't have a way of saying t of n is clearly in theta of something. Well, let's just try to do exactly the same thing again, but with n-2. So we've done this once. Let's do it again. I'm going to do this in a different color, just so we can easily differentiate what's going on. We're going to plug n-2 into star. If I do that, I get t of n-2 is equal to Plugging n minus 2 into this equation for n, I get t of n minus 2 is equal to c2 plus t of n minus 2 minus 1. So t of c2 plus t of n minus 2 minus 1. Then do a bit of algebra. We get t of n minus 2 is equal to c2 plus t of n minus 3. We're then going to replace n minus 2 in the equation we just developed. So replace t of n minus 2. We then replace t of n minus 2. And just to emphasize exactly that we're doing the same thing, this t of n minus 2 is the exact same as that t of n minus 2. So we're going to replace the t of n minus 2 with the right-hand side of that equation in purple. So replace t of n minus 2, and you get t of n is equal to 2c2 plus t of n minus 2, but I am replacing that with the right-hand side, which is going to be c2 plus t of n minus 3. T of n is equal to 3c2 plus t of n minus 3. And now we have another way of writing t of n, which still isn't necessarily helpful. I have this problem where I have t's on both sides, and I can't solve for it. It's not like I have t of n and can just do some algebra and collect together constants. There are different things plugged into them. But we know one other fact that's yet to be relevant. We've had, at the very start of this problem, if you remember, identified this base case to the recurrence. If, somehow, magically, I could make this right-hand side 0, so if we could make this t of 0, which it's not yet, then I would be done. How can we do that? Well, what if we try and identify a pattern in what's happening here so we can get some sort of generic expression? We actually did this exact same thing with while loops. We built a table and tried to identify a pattern and then solved for how many times did the while loop execute. We're going to do something incredibly similar here in that we are going to try and identify how many recursive calls are made. So what we're going to try to do is write down an equation that says t of n is equal to something with a variable. So we've done this in the past. So for any value of k, just like we did with a while loop, we're going to use some variable k to express some pattern. So for any value of k greater than or equal to 1, well, let's look at what each of our different expressions for t of n looked like. We had t of n is equal to 3c2, t of n minus 3. We had t of n is equal to 2c2 plus t of n minus 2. And we had t of n is equal to c2 plus t of n minus 1. If you notice, there's some nice things occurring in this. In the first equation, we have 1 being subtracted and 1 multiplying by c2. In the second equation, we had 2 being subtracted and 2 multiplying by c2. In the third equation, we had 3 being subtracted and 3 being multiplied by c2. So I'm very comfortable conjecturing that t of n is equal to k times c2 plus t of n minus k. So I have now an expression that has a variable and says that for any amount of times that I repeated this process, if I kept plugging back in and plugging back in and plugging back in as I was doing here, I could do this any number of times and get this expression. Why is this helpful to me? Well, I know off to the side, we know t of 0 is equal to c1. And now I have an expression inside of t, which is for any value of k. If I chose a very special value of k, let's say we chose k such that the inside is equal to 0. If we did that, we can use that fact. So we want to choose k such that, so we know that t of 0 is equal to c1, so we choose k such that, s.t for such that, the thing inside there that I highlighted, n minus k, is equal to the value I need to plug into t, which is 0. And let's try to find out what value of k that is. This is really easy algebra. Add k to both sides, and you get k is equal to n. So if I go back to my equation over here, if I replace k with what it's equal to now, I'm going to choose it to equal n. We have n times c2 plus t of n minus k, which by definition over here is equal to 0. We replace it with 0. And look, we know what t of 0 is. We even wrote it in orange over there. T of 0 is equal to c1. So we have t of n is equal to c2n plus c1. So that is an expression now for t of n. And hopefully, if you look at that at this point in the class, you go, I can easily see that that is in theta of n. So thus, my final conclusion is that t of n is in theta of n. And that is a runtime. So let's review the sort of methodology that we used here. If we zoom out, what we did is we first, in the problem, developed what we call a recurrence relation, a way of relating t of n to a smaller value of t. So this thing here is what we call a recurrence relation. Recurrence relation. This is also sometimes called a difference equation. We won't really use that terminology, but there's an entire field of study that involves difference equations. We develop a recurrence relation. We then plug in whatever values are on the right-hand side back into the equation over and over again to identify a pattern. So in this case, that involved plugging in n minus 1 and n minus 2 back into that equation twice. We did that twice, and then we tried to identify a pattern between all of these different expressions that we developed. So our pattern was, in this first case up here, we had k is equal to 1. That was our first part of the pattern. Down here we had k is equal to 2. That was our second part of our pattern. And down here we had k is equal to 3 for the third part of our pattern, and tried to identify what is a generic expression for t, just as we did with while loops. Actually, we did this exact same thing for while loops. Once we had that generic expression, we chose a special value of k and used that value of k in our generic expression to try to analyze it. This methodology is going to work for a surprising number of things and is going to be incredibly useful for us going forward.